Hi guys, welcome back. This is part 2 of our lecture on analysis of variance. It's the 8th lecture in the Core Skills Experimental Design and Analysis section. I should explain that in the first part I realised that I didn't have my lapel mic on, so the sound might be a bit tinny and distant, and apologies if I've now blasted your ears off because you had turned the volume up and we've now got, hopefully, clearer sound from my lapel mic. Anyway, we were talking about analysis of variance before the break, and I gave you the basic principles. Now I want to dive into an example to try and help you sort of remember and understand the principles and see how they work in practice. So we're going to look at an absolutely classical example of a bit of biology, evolutionary biology, which is Darwin's finches. So if you might remember this, that Darwin on his travels discovered all kinds of interesting things, but one of the things that he saw that really helped to cement his ideas about evolution by natural selection was this amazing diversity in the Galapagos Islands of these finches. So you have different finches on different islands, each of which looks slightly different, seems to feed on slightly different things, has different morphology. And Darwin reasoned that what had happened was that an ancestral finch had arrived on these islands and then diversified, occupying slightly different niches on different islands depending on what was available in terms of food and the environment. And what you therefore saw was a process of speciation, separation of these different lineages of birds into new species. So this is a really well studied group of species for lots of different reasons, but obviously inspired by Darwin. And in fact, what you can see on the slide here is images of the different skulls of different species of Darwin's finch. They're actually known as Darwin's finch. And you can see they're quite different. You've got some really big species with big heads and really heavy bills, and others with like pointy hooked bills, and others with really fine, small, delicate bills. And these appear to be adapted, or this is what Darwin reasoned, adapted for feeding on different kinds of food. But of course, we're good scientists. We want concrete evidence. We don't just want speculations of a 19th century naturalist, although he was pretty good at speculating. So let's have a look at some data corresponding to these species and ask a statistical question which will give rise to a biological inference. So let's imagine we've looked at, and this is obviously based on a real study, we've looked at 5 different species of these Darwin's finches, known as ground finches, each with a different bill shape. So we've got the large ground finch, which is a bigger bird, and it's got this big heavy bill, whereas you've got some of these smaller species with really nice fine bills. And the hypothesis we have really here is that these bill shapes in some way correlate with the kind of food that's available and eaten by these bird species. In other words, that the bill is adapted through evolution in order to access the food that's available on the different islands. So putting that in terms of a statistical hypothesis, we would obviously start with the null hypothesis. So the null hypothesis is that there's going to be no differences among these species in terms of the sizes of the seeds they've eaten. So that's the data we're going to collect. We're going to look at the food that these birds are eating, the sizes of the seeds, and our null hypothesis, the kind of boring nothing's going on hypothesis, is that the seeds are going to be the same. Of course, the thing we're interested in is whether there really are differences that correspond to these different bill shapes. So we go out in the field and we collect a bunch of data on the seeds that are being chosen by these birds in the wild. And I've given you some example data on screen. Here we've got 5 seeds for each species measured in millimeters. And even eyeballing the data, you can spot that there might be some patterns here, but we need to know whether those patterns are real. And the first thing we can do is to visualize them on a graph, because that is often a really great way of showing what sorts of patterns might be present. So I've plotted an error bar graph here with the mean seed size plus or minus the standard error, which is the error bar. And you can see that there's a bit of variation here. We've got a couple of species, the sharp-beaked ground finch and the small ground finch, which seem to feed on rather small seeds, just a couple of millimeters, whereas we've got a couple of finches that seem to feed on much larger seeds, more than twice as big in fact, on average. And then the medium ground finch, as its name suggests, is somewhere in between. So this is all very well, and the fact that the error bars don't always overlap is indicative that some of these differences are probably significant, but we want to actually put an objective p-value on that in order that we can say whether or not the differences are real. So that's what we're going to do using analysis of variance. So if you remember, I said that the principle of analysis of variance is to look at the within group variation and compare it to the among group variation and ask whether the differences you see among the groups are greater than you would expect, given how much scatter variation there is within each group. Obviously, if each group is hugely variable within the group, you'd expect the means of the different groups to be quite far apart just by chance. So how do we do that? Well, we quantify the variation. And if you remember, this word variance actually means something mathematically. So the variance S squared of a sample looks like this. It's the sum of the squared differences between the mean and individual data points. So for each data point, we calculate the difference from the mean, square it, add them up, and divide it through by the sample size, corrected for some mysterious reason by -1. But that doesn't matter. The principle here is we've added up the sum of squares, the total amount of variation in the data set, and we've divided it through by the sample size, so we've got the average amount of variation per data point, albeit expressed in squared units, hence the variance is S squared. Squared because we had to get rid of those minus signs so that when we added up the differences we didn't cancel out all the positives with the negatives. So that's the variance, and the top part of that equation is the sum of squares. So when we're talking about analysis of variance, in a kind of way we're talking about really actually this analysis of sums of squares, because that's what we're going to focus on, just that bit on the top, the sum of the squared differences between data and the mean. And we can actually calculate the sum of squares within groups and among groups. So to calculate the sum of squares within groups, well, you already know the equation for that. For each group, we can just use this sum of square equation, and we get our measure of within group variation. We'll get a different one for each group in theory. But in order to get the total amount of variation within groups in the whole experiment or whole set of observations, we need to then add that up across all 4 groups. So we just put another sum sign in front of this. It starts to look a bit messy, but what we're doing is we're calculating the sum of squares for each group where there are n data points in each group. And then we're going to add that up across all of the groups that we've got, from the first group to however many groups there are, which we'll call A in this case. So in our case, on screen I've got 4 groups. In the finch example, we've actually got 5 groups, 5 different species. So for 5 different species, we're going to add up the sum of squares within each group, and then that gives us the total within groups sums of squares. So here's just some flags to say what I'm talking about. J here is the group number or species number in the finch example. X bar, remember, is the mean of the group, not the grand mean. We're going to come to that in a minute. So in order to calculate the other kind of variation we have, the variation among groups, what we're going to do is we're going to take the difference between the grand mean, here we go, that's X bar bar, and each of the individual group means, and we're going to square that. So this is the measuring the difference between an individual group mean and the grand mean. We're asking how scattered are the group means around the grand mean. So we take that difference, we square it just as we did before, because some will be negative and some will be positive, and if you add them up without squaring, then you'll end up with the negatives cancelling out the positives. So if you square them, add them up for the A groups that you've got, in our case 5 species, then you'll have the among group sum of squares. But in order to make sure that it's kind of fair, that it's expressed in similar quantities to the within group sum of squares, we actually multiply it through by the sample size within each group, which is n. So if we've got 5 data points per species, then n is 5. So that's the equation for the among group sum of squares. And by the way, this is about the most mathsy these lectures get. I think it's helpful actually to understand the principles of ANOVA by looking at the equations. For some of the other tests, I'm not so worried about showing you the equations. I'm not going to get you to do maths in the exam, but I might show you a sum of squares equation, for example, and get you to tell me what the point of it is. Okay, so we've got the among and within group sum of squares. What are we going to do with them? Well, actually, let's go back to our example and actually calculate them. So here are our data. So we can calculate the group means. So for each species, the average seed size. So if you remember, we've got a couple of species feeding on big seeds, 4.5 mil here, and a couple of much smaller seed-eating species. Calculate those means, and then to calculate the within group sum of squares, we use that individual group mean, X bar, and we take the difference from each of the data points. So for the first data point, 5.54, we're looking at the difference between the data point and the mean, squaring it to get rid of the minus sign, and then adding it to the next one, and the next one, etc., etc. Just so happens that my second data point is identical to the mean, and therefore the difference is 0. So I top those up for all of my samples, and I end up with a within group sum of squares, which happens to be 26.14 in this example. And then I need to calculate the among group sum of squares. So in order to do that, I need those group means again, but now I need the grand mean as well, the total average seed size for the whole experiment. So that happens to be 3.14. And I need to know the sample size per group, which is 5 in this case. So then I take the difference between the grand mean and the group mean, and I square it to get rid of the minus sign. I'm going to do that for each of the groups in my sample until I get the total amount of differences between the means and the grand mean, and then I multiply by the sample size 5 to get my final number, which is the among group sum of squares, 28.47. So a bit of kind of mathematical jiggery pokery going on here, but the sort of learning outcome here mostly is about the principle. The principle is we can use this simple maths to calculate the total amount of variation within groups in our experiment and the total amount of variation among the groups. And then we're going to ask, is that amount of variation, this sums of squares among groups, greater than we'd expect given the amount of variation we've got within groups? So to sort of make sense of all of this, it's helpful to create a table to put your sums of squares in, and this is called an ANOVA table, and this is particularly helpful when the examples get more complicated, which they do, although in this course we're not going to look at too much more complexity. We will look at a slightly more complicated example. So an ANOVA table basically bungs in the information we've just got and eventually is going to include a p-value, which is going to test our hypothesis. So first of all, we can chuck in the sums of squares that we've just calculated for among groups and within groups. And we can also show the total of those sums of squares, add them together, and that gives us an index of the total amount of variability in the whole data set, regardless of whether it represents within group variation or among group variation. We can then chuck in some degrees of freedom, which, if you remember, are these sort of rather mystical values which represent the sort of power of the analysis. They're normally related to the sample size. So the degrees of freedom for the among group variation is the number of groups, A, minus 1. So we have 5 species in our bird example. Minus 1 is 4. That's the degrees of freedom among groups. The degrees of freedom for within groups is slightly more complicated. It's the sample size of each group, which in our case was 5, minus 1, so n equals 5, minus 1 is 4, multiplied by the number of groups, which in our case is 5. So 5 times 4 is 20. And we can also calculate the total degrees of freedom too. So a key thing to remember at this point from earlier lectures is that the sum of squares is a thing that just keeps on getting bigger the more data you've got. So we want to sort of control for that by dividing it through by something, by dividing it through by the kind of sample size. So in this experiment, or study, the more species we've got, the more data we'll have, and also the more samples within each species we've got, the more data we'll have. So we've got 2 sort of sources of extra data. So what we do is we take the sum of squares and we divide it by the relevant degrees of freedom to get a sort of average amount of sum of squares per degree of freedom. And that thing is called, the answer to that is called the mean square. So that's the other thing that you'll see in these ANOVA tables that is a bit mysterious. It's called the mean square, and it's the sum of squares divided by the degrees of freedom. Easy enough to calculate in our case. First one is 7.1, the next one is 1.3. So once you've got the mean squares, they have known mathematical behavior, and in particular their ratio has a known mathematical behavior. So we calculate the ratio of one to the other, basically divide one by the other, and that thing is called f, the f ratio, and it has known mathematical behavior. So just like the t statistic has a distribution that we understand under the null hypothesis, the f ratio has a known distribution under the null hypothesis. I mean, we could draw it on a graph if we really wanted to, but I'm not going to. And once you've got a statistic like f that has known behavior when the null hypothesis is true, that allows you to calculate p, the probability of a particular value of f, given a particular sample size, if the null hypothesis is true. And if you remember, that's basically always the target of a statistical test, is to calculate p. So we need to calculate that ratio of mean squares first. So we calculate the ratio of the among group to within group sums of squares. 7 and a bit divided by 1.3 gives us an answer of 5.4. So that's the F statistic, or F ratio. And it's the thing that if you plug it into a computer, or in the old days if you looked it up in tables at the back of your stats book, you would then be able to generate a p-value. So when F is big, just like almost all statistics, when F is big, that indicates a big difference or a big deviation from what you'd expect under the null hypothesis. Why is that? Well, what does it mean? It's the ratio of a quantification of the among group variation, that's the interesting differences between the groups, versus the boring within group variation, which is just caused by random differences among individuals. So when this ratio is big, when the top number is big compared to the bottom number, then what you're looking at is relatively big differences among groups, given how much variation there is within groups. So a big value of F indicates a possible deviation from the null hypothesis. These data don't appear to be consistent with the null hypothesis. And obviously you don't know how big is big, the computer's going to work that out for you by putting a p-value on it. So the answer for this particular study, for that F ratio of 5.4, is a p-value of 0.004. So there's a 4 in 1,000 chance, or a 0.4% chance, of you observing an F ratio that big, given the sample size and the number of groups as reflected in the degrees of freedom, and given the null hypothesis. The null hypothesis says that among group variation just arises as a result of random chance, because every individual in the study is different, and therefore, of course, if you pick out 5 individuals at random, you'll get a slightly different mean each time. So that's the null hypothesis. That's the boring thing it says is going on. And our F ratio says, well, that's extremely unlikely to happen, less than 1% chance, if the null hypothesis is true. And so we would reject the null hypothesis and conclude the null hypothesis is not true. So just to reiterate, in order to calculate the p-value here, and you're going to use a computer, you need the F ratio, but you do also need the degrees of freedom, because that tells you about the power, the sample size that you've got. Not just the sample size within group, but you also need to know how many groups you've got, so you need the among group degrees of freedom as well. So when you present an F ratio in a report or in your write-up or whatever, you would normally quote, or you would always quote, 2 degrees of freedom, the degrees of freedom among groups and the degrees of freedom within groups. And for a given F ratio and given degrees of freedom, the computer will calculate your p-value, and that tells you whether or not you should reject your null hypothesis. So in our case, we would reject the null hypothesis and conclude that there are significant differences in seed size among the different species that we've looked at, which is probably not surprising given what the graph looks like. And it's true that most of my examples in these lectures tend to be significant, because kind of significant things are a bit more interesting than non-significant things. Anyway, we've rejected that null hypothesis. Great, we've finished the job, maybe. But actually we haven't. So we're going to come back after the break, and we're going to look at a way, what we can do beyond what we've just looked at, to address the question of, well, which species are different from which? Because so far all we've concluded is there are differences, and that's only half the story.